Recent discoveries from the James Webb Space Telescope are shaking the foundations of cosmology. These findings challenge our deepest assumptions about the nature of time itself, leading scientists to reconsider the very fabric of reality. The more we observe, the more we realize how much remains unknown, and each new revelation forces us to rethink fundamental principles. The standard model of cosmology suggests that the universe's expansion is driven by dark energy, a mysterious force that constitutes about 70% of the cosmos. However, new data suggests an alternative explanation, one that may not require dark energy at all. This possibility challenges decades of theoretical work and pushes scientists to seek a new paradigm to explain cosmic behavior. When astronomers analyzed JWST's high-resolution images, they discovered galactic structures and spatial arrangements that defied expectations. These observations suggest that our traditional understanding of time and expansion may be incomplete or even fundamentally flawed. The complexity of cosmic structures reveals that the universe may be governed by principles we have yet to fully grasp. In response to these unprecedented findings, leading cosmologists convened at the Royal Society in London. They debated whether our long-standing cosmological assumptions could still hold in light of these revolutionary discoveries. Some argued that while the standard model has worked well, it must evolve to incorporate these emerging anomalies. Subir Sarkar, a cosmologist at the University of Oxford, argues that the current theoretical framework for cosmology is outdated. He emphasizes that although modern telescopes provide unparalleled observational data, our theoretical models remain rooted in a century-old perspective. He believes that a radical shift is necessary to explain the mounting inconsistencies. The discovery of the universe's accelerated expansion in the late 20th century led to the introduction of dark energy. Scientists inferred its presence due to the unexpected speed at which distant supernovae were moving away from us. But what if the nature of time itself accounts for this expansion rather than an unseen force? The lambda CDM model has long been considered the best explanation for cosmic expansion. However, JWST's observations reveal inconsistencies that question whether this model can fully explain the structure and evolution of the universe. The discrepancy between theoretical predictions and observational evidence suggests that we may be missing a crucial component in our understanding. If dark energy were truly responsible for expansion, the universe should be uniformly expanding. However, astronomers now see evidence that certain regions of space expand at different rates, contradicting this assumption. Such variations imply that the forces governing cosmic evolution are more complex than previously thought. A recent survey of 1.5 million quasars revealed a slight imbalance in their distribution across the sky. This suggests that the universe may not be isotropic, as traditionally assumed, adding further complexity to the problem. The existence of large-scale structures at such immense distances challenges our perception of the universe's homogeneity. Cosmologists have identified vast regions of emptiness, known as cosmic voids, which are more extensive than our models predict. These structures further complicate our understanding of cosmic expansion. If space is more varied in its composition than expected, then our understanding of fundamental forces must be adjusted accordingly. Timescape cosmology proposes a radical rethinking of the nature of time itself. Instead of being uniform across the universe, time may flow at different rates depending on the density of matter in a given region. This concept suggests that time dilation, rather than an external force, may explain some of the apparent acceleration in the universe's expansion. In this model, clocks in densely packed galaxies tick slower than those in empty cosmic voids. This means that different regions of space experience time at different rates, fundamentally altering how we perceive the age and expansion of the universe. The implications of such a concept extend beyond astrophysics and into fundamental physics itself. While traditional estimates place the universe's age at 13.8 billion years, Timescape cosmology suggests that the age of the universe may be variable. Regions with little matter may have aged much more rapidly than dense regions. This redefinition of cosmic time challenges the notion of a singular beginning or a unified cosmic timeline. If time is not a constant across the cosmos, then the idea of a single, universally agreed upon age for the universe may be meaningless. Instead, time itself may be relative to an observer's location. This raises profound questions about the nature of history, causality, and the very structure of the physical laws we rely upon. If voids expand faster than dense areas, then the perceived acceleration of the universe's expansion may be a consequence of our vantage point rather than a fundamental physical law. This perspective aligns with observations that suggest regions of space experience different expansion rates, leading to the illusion of a uniform acceleration. Researchers at the University of Canterbury compared observational data with predictions from Timescape cosmology. The results suggested that this model may provide a better fit to actual cosmic expansion trends than the lambda CDM model. If confirmed, this would necessitate a re-evaluation of some of the most basic principles of cosmology. One of the most surprising implications of timescape cosmology is that the Milky Way itself may reside within a cosmic void. If true, this could explain discrepancies in our measurements of cosmic expansion. A void-like environment could alter local gravitational effects, leading to misleading interpretations of cosmic data. The KBC Supervoid, a region of space spanning nearly 2 billion light-years, has been proposed as the largest known cosmic void. Some researchers argue that its presence could account for anomalies in our cosmological observations. If voids play a major role in shaping the universe, then their impact on cosmic evolution must be thoroughly investigated. The Hubble tension refers to inconsistencies in measurements of the universe's expansion rate. If the Milky Way is inside a supervoid, our local measurements may differ from those taken elsewhere in the cosmos. This could mean that different parts of the universe exhibit different behaviors, requiring a more localized approach to cosmology. Observations show that galaxies within and around voids move in unexpected ways. This contradicts predictions made by the standard cosmological model, suggesting alternative explanations are needed. The challenge now is to refine existing models to account for these deviations without discarding well-established physics. Using advanced simulations, researchers have created models to better account for bulk flow anomalies and variations in cosmic expansion rates. These models integrate various factors, including gravitational lensing, matter distribution, and relativistic effects. If different regions of space expand at different rates due to time variation, then our understanding of cosmic acceleration may need to be completely revised. Such a revision would impact our theories on dark matter, energy distribution, and even the origins of the universe. If timescape cosmology holds, then dark energy may not be necessary to explain the observed expansion, as differential time rates naturally account for the phenomenon. This possibility excites many scientists, as it could simplify our understanding of the universe while removing an element that has remained mysterious for decades. Observers inside voids perceive an accelerating universe, while those outside may see a very different cosmic picture. Perspective plays a crucial role in cosmological interpretation. This suggests that our measurements must be contextualized according to where we are within the universe. Future missions by JWST and other telescopes may provide the definitive data needed to validate or refute timescape cosmology. With continued advancements, new instruments may detect evidence that confirms or disproves these groundbreaking ideas.